today we will discuss linear signal models. We are trying to get closer and closer to the actual problems, but still there is something to understand before we can actually handle the problem of estimation. We have not yet arrived at any estimation problem so far. So we will begin with the question of what is a signal model. A signal model, simply stated, is a mathematical way of describing a signal. We may be describing, in some cases we may be interested in describing the signal values themselves. For example, I mean a very simple, this pens create trouble. For example, we write that, say, let us say when we describe a signal as a Fourier series, right. So we say that the signal xt, any periodic signal xt, can be broken up as xt e to the power minus j omega t. Actually it should be written as, if it is periodic, it can be written as k omega 0 t. K is equal to minus infinity to plus infinity. So what are we trying to do? We are trying to express, rather no, this is not xt, this is xk. So we are saying that a signal which is periodic can be expressed as an infinite sum of some complex exponentials, which are like you know, in our earlier classes we write in terms of sines and causes. If we add them together, we can write in terms of a complex exponential, j k omega 0. K is an index which varies, which denotes the various frequencies, and e to the power j omega 0 can be written as sine and cos. So what are we trying to say? We are trying to express a signal in some mathematical form. So a Fourier series is a kind of signal model. So is a Fourier transform. So this is a deterministic signal model. If we try to model random signals, then we cannot express values, because there are no values. Signal can be something depending on the outcome of the experiment. Then what we try to do is, in the case of random signals, we try to either characterize its autocorrelation function. Since it is an ensemble average, so it becomes a deterministic function. So there we are trying to characterize some property of the system, of the signal, because the values of the signals cannot be directly described. Similarly, we can describe, corresponding to this, we can write its power spectral density, which is another mathematical description, only written in terms of omega now. So in each of these, we are trying to describe either the signal values themselves or some of its properties in a mathematical way. That is a signal model. So why do we have to understand signal models? Because signal models are going to be very much used in our course. We will always be dealing with certain kinds of signal models for the purpose of estimation. Why do we need signal models for the purpose of estimation? For various reasons. For example, suppose we have discussed that problem of active noise cancellation. So if we want to do that, then what do we essentially need? We essentially need to predict what is the next signal of that is the noise which is being created, what is going to be its amplitude and phase in the next instance, so that we can create another signal which will destructively interfere with that and then reduce the noise. So essentially what is involved is a prediction. So some prediction of the next noise signal value is needed so that we can cancel it. Now how are we going to predict it? We will predict it using some mathematical form based on its past values. So the moment we try to do that, we are going to need a model, because we must have a computational rule by which we are going to say that since these noise samples occurred in the past, that or if we know that the noise that is being created has this kind of characteristics, if we are given that, then we must have a rule of calculating what signals we should generate such that the noise is cancelled. So we need to describe properties of signals. That's why we need signal models, right? Similarly, suppose we regularly do when we let us say send a speech signal. Let us say we describe the concept of voice recognition systems. So voice recognition systems, once you speak something to the system, from that signal sample it tries to recognize who is the speaker, right? So how does it do that? It does that because it tries to extract, it has already some properties of the speech signal of a speaker has been stored in the system, and when a given speech signal is supplied to the system, then it creates a signal model for that speech signal. For example, suppose it will try to model the power spectral density of the speech that you have given to it. Now it knows that what is the nature of the power spectral density of Mr. X. So you see, it has got a model of a signal that it has got. It already has a model stored of various speeches of Mr. X, and then it tries to compare the models, because the signal values of a speech signal, if you actually record a signal, it can be done very easily in the PC, and if you plot it, even if you say the same sentence n number of times, at none of the times the signal values are going to match. Similarly, when you want to transmit speech signals to a long distance, let us say over a network, you don't transmit each and every signal value, because that is going to take a lot of bandwidth. So what you do is you actually create a signal model out of that speech, and you transmit only the properties of that model to the other end, and then using those model coefficients, you recreate the signal. You don't send the signal every sample by sample, because that will take too much of communication bandwidth. So for all these kinds of problems, you need to create a model of a signal. Without a model of a signal, you cannot do anything virtually. So that's why all our estimation problems we will pose in terms of a signal model. So we need to understand what are the typical commonly used signal models and some of their properties. It itself is a somewhat vast area, but some of it you are already now learning in some of the other courses, like for example you are doing DSP, so some of what I am going to talk about today you will do in much detail in DSP, and some of it you may be doing in linear systems course and things like that. So we will sort of scan over just to be able to start our estimation problems. So typically speaking, signals are of various types. They can be, this is just one classification, you can have various types of classification for signals. For example, you can have a continuous, these are very important classifications. One is continuous time, another is discrete time. When you are talking of a discrete time signal, you are only given the values at certain points, and you do not at all know the values at the other points, right? You can make certain assumptions about them, but as such, when you are dealing with a discrete time signal, whatever you are doing filtering, whatever, I mean all that you do in DSP, you are actually talking about only those points of time. At the other instance of time between sampling instance what is happening, we are not so much concerned. Of course, they come because I mean real signals have to be continuous time, but they come through other means. In the core cases, you will always be talking about the signal at certain points of time, and such signals are called discrete time. Similarly, as we have seen that we may have deterministic signals or random signals. Typically, in this course, we will be talking about this particular combination, that is random discrete time signals. Right? Now, random discrete, this is just to recap. Typically, as I was saying, that you can have, for example, if you have a periodic continuous time signal, signals can also be classified as periodic and aperiodic, let us say. So, if you have this is one of the earliest signal models that we learned so far in our engineering. So, if you have a periodic continuous time signal, then it can be expressed as a Fourier series, and the Fourier components can be obtained from this integral. This is well known. Similarly, but what if the signal is aperiodic? If the signal is aperiodic, then you cannot express it as a Fourier series, but rather you have to express it as a Fourier transform. So, for an aperiodic signal, this is a Fourier transform, which we are so familiar with, and you can again get back the time signal using what is known as the inverse Fourier transform. Similarly, for discrete, exactly similarly for discrete periodic signals, you can have a periodic, you can have a discrete Fourier series, where now I am only talking about n. Here I was talking about t. T is a continuous variable. Here n is a discrete variable. I mean numbers like -2, -1, 0, 7, only integers. Okay. And similarly, it's so these are the discrete Fourier components, and this is the, I mean you can get the this is how a signal's time values can be expressed in terms of its Fourier components, and if you want to express the Fourier components, if you want to compute the Fourier components in terms of the sequence, actual time sequence of the signal, then this is the inverse Fourier series. Similarly, again, so just like here you can have an aperiodic signal, here also you can have an aperiodic signal. You can have an aperiodic discrete time signal, which is not periodic, which does not repeat itself. In which case you have to define, this is known as the celebrated discrete Fourier transform, or DFT. So the discrete Fourier transform is actually defined like this, and you can again get back the sample values from the discrete Fourier transform using an inverse DFT. Okay. So these are some of the very early signal descriptions which are constructed, and I mean Fourier transform is so important because it is analytically simple as well as enlightening to study signals not in the time domain but in the frequency domain. Okay, so I mean studying signals in the frequency domain is so popular because we can very simply understand some of its properties, which is very difficult to visualize in the time domain. Okay, so now since we are basically concerned about discrete time signals in this course, so we have to, it is good to understand the connection between the discrete time signals and continuous time signals, because after all what we see in real life, everything is continuous time, right? There are discrete time signals as well. I mean there are discrete time quantities, right? Like for example, if you take the stock market, let us say the BSE index at 10 o'clock every day for n number of days, it will form a discrete time sequence, right? That since that essentially even physically it does not have a continuous time counterpart, it is an inherently discrete signal. But normally the physical signals, current, voltage, temperature that we see are essentially continuous time. But when we create a discrete time description of them, and when we deal with them, which we will do so often, because especially in the context of this course, because whenever we are talking about signal processing, we are generally talking about physical signals. I mean signals like voltages and currents typically. Okay, so such signals are I mean inherently continuous time, but still will deal with their discrete time description. So we need to understand what does this discrete time description actually mean, right? So we need to understand that, I mean, the discrete time description is actually obtained from the continuous time description by a process called sampling, right? So when we say xn, what we actually mean is x, I mean c for continuous, that is there is a continuous time signal xc of t of small, these pens give you. So actually there is a continuous time signal xc of t, and you are merely sampling it at t is equal to t, 2t, in general nt. So we are talking about a periodic sampling here, and then when we say xcn, what we actually mean is that xct at t is equal to nt. That is what we mean. Okay. Now the question is that, so fine, so this is how the discrete time signal sequence and the continuous time signal are related. So a very I mean a very valid question is to ask that how are their transforms related, because we can easily construct a DFT of this discrete time sequence. We can also construct a Fourier transform of this continuous time sequence. So how are those two related? That is a very important question to ask, and it has, I mean, there are very, I mean, some of the most beautiful and profound results of signal theory are, I mean, actually relate to that. So it says that this is a very fundamental result. This, what does it say? It says that if you sample a signal at a sampling frequency fs, these things will be, I think, will be covered in much more detail in your DSP course. We cannot, this has a great deal of mathematics on it. We cannot do that. What we will do is we will learn the result and we will understand the, I mean, understand the meaning of the result without actually going through proofs and other things, right? So this says that, now the question is, a very important question is that if you have a continuous time signal and if you are going to take samples of it at certain instants of time and then work with the samples and then arrive at certain results, are those results going to be valid for the actual continuous time signal? We must ensure that the results that we arrive at using the discrete time sequence are actually meaningful in the final real world. If that does not happen, what is the use of using the discrete time model? So we say that, now that has, so what do we mean by it has meaning? What we mean by it has meaning is that, first of all, that suppose we take a signal, okay? So we take a signal and this pen is giving me trouble. So what we mean is that suppose we have a continuous time signal and we have taken samples of it. So we got a sequence. Now we are going to manipulate that sequence. We will say that suppose a signal is, suppose the actual continuous time signal is passed through a filter. So it will go, so I will get some other signal at the output. Now the point is that I need to know that how can I use this sequence and pass it through some other box which we call a digital filter and get another sequence out, and that sequence should actually match the sequence of my analog filter which is fed by the analog signal. We ask such questions because unless they match, what is the point of digital filtering? So it turns out, first of all, the first question to ask is that once I have sampled a signal, if I am given a sequence, from the sequence can I go back here? Going back from here to here is very simple. Just pick up some points. But given the points, can you get back the original signal? So that is called the problem of reconstruction. Now it turns out that, as we know, this is the famous Nyquist theorem, which says that it is theoretically possible. Remember the word theoretically, because even if you said it is theoretically possible if what does it say? It says that if this signal has a frequency spectrum which is limited to, let us say, some f, capital F, that is this signal spectrum, this signal has no other frequency component more than f, then if you sample it at greater than or equal to twice f frequency, then you can theoretically reconstruct it from the samples using some reconstruction functions which are called sinc functions. That is, but remember that you cannot practically do it. You can be approximately correct, but you cannot practically do it because even the reconstruction process involves an infinite number of terms to be added. So it is not practical, but the importance of the result is that if you sample at lower than 2f, then you cannot even theoretically do it. It is not possible, right? So the first thing is that if you want to sample, we have to ensure two things. First thing we have to ensure is that the signal that we are sampling is band limited. So it has a bound on its frequency. If its frequency content goes on and on and on, you cannot sample it. At whatever rate you sample it, you are going to have trouble. That is why we put what is known as an anti-aliasing filter. We put an anti-aliasing filter just to ensure that the signal that I am sampling is bounded in its spectrum. Its bandwidth is bounded, right? Second thing that you have to do is after that. So now when you have put an anti-aliasing filter, you know that its bandwidth is restricted. Now you can sample at twice the bandwidth or more. Actually, practically speaking, you should do it at 5 to 10 times the bandwidth. But theoretically speaking, you should at least do it twice, so that the samples that you are getting is a faithful reproduction. See, what is the idea? The idea is that suppose you have got these samples. So what tells you that that in between two samples the curve is going to follow this and not this? How can you be sure? So you can be sure because you have put a frequency restriction on the signal. So if between two samples which are twice the bandwidth frequency, if it has to have a component like this, then the frequency component of the original signal must be higher, but you have limited its frequency component. So such widely varying signals are not possible. That is the basic logic. Okay. So that is so we have to remember these things. Although in our course we will never encounter it. We'll not even mention capital T. This capital T. We will always talk about xn. But we must remember that if we do not keep this in mind, then we are going to have serious trouble. What is the trouble? See, the trouble is that suppose this signal has a bandwidth of this, that is a spectrum of frequency spectrum of this, that is this is ft and this is say mod fj omega. The phase plot I have not done. This is omega. Okay. Now we are now coming back to the original question, that is what is the relationship between the discrete Fourier transform of the discrete sequence and the original Fourier transform of the continuous sequence? What is their difference? So this is the continuous signal, this is fj omega, that is the continuous Fourier transform of ft. It turns out that if you take the discrete Fourier transform of this sampled signal, then that Fourier transform will look like this. That is, it will be this band only, but it will get repeated. It will go up to infinity. Even if this is band limited, this is not going to be band limited. This will continue. It is actually very easy to see why it will continue. It actually continues because of the basic property that after all x e to the power j omega, which is the Fourier transform, is sigma xn e to the power minus j omega n. No, this is the it will be no, this is it will be sigma k is equal to minus infinity to infinity xn e to the power minus j omega xk e to the power minus j omega k. Right. Now, you see this function is necessarily periodic in omega, because this function itself is periodic in omega. So therefore, the value of x e to the power j omega must repeat from whatever value you get from 0 to twice pi, you will get the same value again from twice pi to 4 pi, again from 4 pi to 6 pi, that will happen. So this must repeat. Now, the problem is, what is the problem if it repeats? Our question is that how I can get back, if I can get back this one from this one, it's okay. So the question is, how can you get back these two? How can you get back this from this? Very simple, use a filter, cut off the other parts, have only one lobe. Now, the question is, when can you cut it off? When they are separated. If this center frequency f, which is basically the sampling frequency, if it becomes less than, actually this is not f, this is actually this will be, yeah, this is the sampling frequency. See, this is the center. So if this is f max, that is the maximum frequency component, then this is going to be twice f max. That is, if this this is right. So if f is greater than twice f max, can you see this? If f is greater than twice f max, then they will be separated. Otherwise, they won't be separated. Otherwise, they are going to be overlapped. That is, it will look like this. If you have f less than twice f max, then after sampling, they will, one curve will be, say, this is one f j omega, another f j omega will be this one. They will actually overlap. So the overall frequency response will actually be, you have to add them, na? So you have to add this index and this, so it will become actually twice. So you see that the frequency response of the actual signal will get totally distorted, and there is no way of getting, once they are mixed up, there is no way of getting this lobe. That is why you should have a sampling time of sampling frequency of more than twice f max, roughly speaking. So this is a fundamental result which we should remember. Similarly, there is also another important thing that we should mention, is that, because these things are not always mentioned in books, and sometimes they are just, they are just glossed over, and they are taken as if they are very natural, but they create some serious confusions. For example, just imagine that you are defining that x e to the power j omega is equal to sigma k is equal to minus infinity to infinity xk e to the power minus j omega k. This is how you are defining the DFT, while the x j omega you are defining as minus infinity to infinity xt e to the power minus j omega t dt. Now, suppose I have xt is equal to x n delta, or rather xk delta t minus kt. That is, I have this signal, at every, say at 0 I have an impulse, at t equal to t I have an impulse, at t is equal to 2t I have an impulse. The strength of this impulse is x0, the strength of this impulse is xt, the strength of this impulse is x2t, and so on. Then if you now substitute this here, what will you get? You will get this. So this is why the process of, so you can say that the discrete Fourier transform is nothing but the original Fourier transform of a signal which can be imagined as an impulse train, a train of impulses, one here, one here, one here. The strength of each impulse will be corresponding to the value of the sample. So a signal is now replicated or rather substituted by an impulse train. Okay. Now this is all very fine, there is no problem. There is one excepting that there is a big problem. What is the problem? The main problem is that the energy of the signal has been multiplied by many times through this process. What is the energy of the impulse signal? That is the area under the curve. The area under the curve of the impulse train and the area under the curve of the original signal are roughly related by t. That is the continuous signal, that is integral x, simply because imagine that samples are here, just I am, so what is roughly the area of this signal? Roughly the area of this signal, if these two are close, I am just drawing it. The area of this curve is roughly equal to this rectangle. What is this? This is the sampling time t. So it is roughly x, say kt into t sigma. K is equal to minus infinity to plus infinity. This is the area under the curve, because each curve you just replace by the area of this rectangle. If these are close enough, then it matches. But what is the area of the impulse train? Area of the impulse train, for each impulse the area under the curve is 1. So it is only sigma x kt, because at each point you have one impulse. So you see that you have, this was the area under the curve of the continuous signal, and this is the area under the curve of the discrete signal. So you have amplified, this t is generally a very small quantity because you sample fast, so the time period is small. So you have, through this, just to sort of, that's why some people, though this is the most commonly found definition of the DFT. Remember that the area under the curves will not match. You have already made an area amplification by a factor of t. That's why some people say that it is better to put a t here, though this is not the usual definition. If you put a t here, then it will match, right? So we must remember this, because in the whole of DSP course this will be referred to without this t. Okay. So this is how the discrete sequence and the continuous signals are related. Now let us see how they get filtered, because that is our prime concern. Okay. So we are talking about linear discrete time systems. So now what we are trying to do is, we are trying to construct a model which will use with the discrete time sequence and get out other discrete time sequences, and they will match realities. That is our objective. Okay. So we will work in terms of sequences, because that is simpler, that is done, that has to be done in many cases, or in all of digital filtering, that's what has to be done. So we know these results. So again, we know that yn will be obtained by a convolution of xn to hn, which is defined like this. Now obviously we are going to be concerned about things like stability, because if something goes unbounded, it's generally of no use. Either it is dangerous or it is of no use. So when shall we say that this filter is BIBO, means bounded input, bounded output stable? That means if you apply a signal, all of whose values are bounded, then you will get output, you will get out and sequence, all of whose values will be bounded. So if you feed bounded input, you will get bounded output. This is called bounded. This is the most general definition of stability. It's called BIBO stability, and it turns out that, remember that we are only talking about linear systems, because unless you have linear systems, this definition does not hold. the convolution integral is basically derived based on the principle of superposition. So we have already made an assumption that we are talking about linear systems. Okay. So if we have such a system, then it will be bounded. It can be shown that if this condition holds, this is called what is called the absolute boundedness of the impulse response sequence, mathematically speaking. So if the impulse response sequence, what is the impulse response sequence? Impulse response sequence is that if you had fed an impulse to the system, and then that is if you feed an impulse here, in other words, if you feed a discrete time impulse, when we talk about impulses, once we have come down from the to the discrete domain, we always talk about discrete time impulse. Discrete time impulse means one of them is a 1 and the others are 0. Then in general you will get a sequence of y. Suddenly output will rise, it will rise, then it will slowly fall, generally speaking. If you give 1 once, the output will rise to some value and then fall. This is what generally happens. So in general we will get sequences of yn. That sequence is called its impulse response sequence. Okay. So if its impulse response sequence satisfies this mathematical condition, then this system is bounded input stable, and vice versa. If it has to be bounded input bounded output stable, then its impulse response sequence must satisfy this. So it's if and only if. Right? This proof is rather simple and it's okay. Now we generally deal with a transform. You see, you must always remember that transforms are just like mirrors. You have a signal. Actually, you have a time signal. You are just seeing the time signal in a mirror because of certain properties. So rather than studying the signal as a function of time, you are studying as a function of omega, because that helps you purely for convenience. Okay. So once we are given this impulse response, we would like to define a transform. So we will now study it in terms of a function of z, because that gives us insight. So we define what is known as a z transform. You can very easily understand that if you put z is equal to e to the power j omega, you get the Fourier transform. But in general, z is not e to the power, z may or may not be e to the power j omega. Z is a complex quantity. It can have a real part also. Now there are certain things which we don't study. Generally we sort of gloss over in our courses. Is that when is this defined? Is it defined for all values of z always? Obviously not. For some values of z, this summation is an infinite summation. It can always blow up. So I mean, if it blows up, you cannot if this summation does not converge to a value, then there is no use of writing an hz. So associated with every z transform, there is a region of convergence. For certain values of z, it converges and it is defined. For certain values of z, it is not defined. We generally don't pay attention to these things especially in our early courses, and we are always talking of tables and inverse transforms and things like that. But we must remember this. Now these are some mathematical results which are basically based in complex analysis theory. So you have to understand, if you read complex analysis, these results can be proved. We are not proving them. Is that for a system to be stable, the region of convergence, that is in the region in which z should take values such that this has a meaning, must contain the unit circle in the z plane. There is a unit circle which we deal with stability. That unit circle must belong to the region of convergence. For example, if this is the unit circle, and if you say that the region of convergence is here, then it is not a stable sequence. Then that system is not stable. But if you say that the region of convergence is this, then it is stable, because it contains the unit circle, right? So why we are talking about these things will be clear very soon. then we are also, so in general, why we are talking about stability, we are always concerned about stability, because stability is a useful thing. It's, as I said, that if something is unstable, it generally serves no purpose. But it has to be stabilized in that case, which is the prime concern of control. Another thing that we are talking about is causality. Things, causal means what? Causal means that output that is nothing can be affected by the future, in short. Things can be affected only by the past. So the output at any time n0 must be a function of inputs for n less than or equal to n0. It cannot be a function of an input which has not yet occurred. You are standing at time t. How can your anything be affected by an input at t plus 10, because it has not yet come, right? So it's a very intuitively meaningful requirement. But this model, it means certain things. It means that when will this system be causal? This system in general is not causal, because this, look at this. What does it mean? What is Hn minus k? Hn minus k is Hn minus k is actually an impulse, its impulse response for an impulse occurring at k. So this output Yn merely says that it is the summation of all such impulses occurring at, so xk is an impulse occurring at k, that will give a response xk into h of n minus k. Now you add up all these responses, then you get the total response. That's what this summation is saying. Now it will turn out that what is this h? Suppose this index becomes negative, that is h of n is not 0 for n negative. Now n negative means what? Means the impulse is occurring at, means that the impulse is occurring, that is the impulse response of a signal which has not yet occurred, because xk is here, suppose xk is positive, but hn minus k is negative. So which means that you are getting responses due to future inputs, right? So if this happens, in this formula there is nothing which says that it cannot happen. So if you additionally impose this condition that Hn equal to 0 for all n less than 0, then you get a causal impulse response sequence. Okay, and we will actually, when we have to derive certain results, why I am saying is that we will always assume implicitly, we may not always say, but sometimes it happens that you cannot, that is you can choose. For example, suppose you are given, it will, I mean I will presently show that given an hz, you can have various impulse response sequences which will give the same hz, but some of them are going to be causal and stable, some of them are going to be non-causal and unstable. In this course we will implicitly always choose the causal and stable sequences, although mathematically speaking you can get any one of them. Okay, so this is a very prime condition which is related to this concept, that is invertibility and minimum phase systems. This invertibility is very much sometimes used by geologists who actually want to understand. They will measure, let us say, ground vibrations, and then they will try to infer what happened 2 kilometers under the surface, right? So you can imagine that the earth behaves somewhat like a filter. So in, say, 2 kilometers below the earth there was an explosion, so something occurred inside, right? Some signal was generated. That signal actually travelled through earth, and you are measuring it on the earth's surface, and you want to know what happened down below, right? So what happens is what you are measuring is Yn, this is the earth, and something happened down below. Now you want to understand, from this you want to understand what happened here. This is a standard geophysical signal processing requirement, right? They will sometimes call it deconvolution. So Yn is obtained from Xn by convolution. You want to deconvolve Yn to get back Xn. This is a signal processing requirement. So the question is, when is it possible? Is it always possible? It is not always, I mean, it is not always uniquely possible unless you make assumptions, and assumptions about stability and causality. If you make an assumption about stability and causality, then you can uniquely determine the xn, not otherwise, right. For example, say, so it turns out that, so the question being asked is, what is this H inverse? Can we think of an equivalent system to which if we feed yn we will get back xn? If we could find it, then we can know what happened down below. So it turns out that now yn is this xn convolution hn, and if it exists, then xn is yn convolution h inverse of n. Again, in another, we are implicitly assuming that if h is linear, h inverse will also be linear. That we are assuming. It so happens that if h is linear and if h inverse exists, it is going to be linear also, right. So now it is, rather than, you know, this double convolution is a bit because I mean it's a bit confusing, because this star is actually a misleading. I mean it actually means an integral. Okay, so though it looks very simple, it is not a product, right? But it becomes a product in the frequency domain. The moment we take z, it becomes a product. That we know, that if we take z transform, then convolution means product. So now obviously what is going to be, so if we just put this, it is going to be xz, hz, h inverse z, which means that hz into h inverse z must be equal to 1. So in the z domain we can very simply find out h inverse z. It is nothing but 1 by hz, right. Now the question is, if it is 1 by hz, what is, I want to finally find out xn. So I have to convolve. For example, if hn is suppose this, delta n minus half delta n minus 1, then hz is this. So what is h inverse z is 1 by this. Now the point is that given that h inverse z is equal to this, can you find out what is h inverse n? It depends on what is the region of convergence you are assuming. If you assume that the region of convergence is greater than half, that is this sum should converge for z greater than half, which we generally assume always in our standard z transforms, then it turns out that h inverse n is this. Un means an unit step function. Un is equal to 1 for n greater than or equal to 0, and it is 0 for n less than 0. So now what does it mean? First of all, see that it is half to the power n. So as n progresses, it comes down. So it is stable. Second thing, it means that, so it is stable means if you evaluate that sigma mod hn up to infinity, this sum will converge. So the system is stable. And secondly, because of this un, you are having that hn equal to 0 for all n less than 0, because un is the unit step function. So for all n less than 0, un is 0, so then hn is 0, rather h inverse n is 0, which means that h inverse n is causal. We just learned that if any impulse response sequence has to be causal, it must be 0 for n less than 0. But you can find out that this exercise you can do yourself, that if you assume that the region of convergence is this, then you can find that this hn will give this h inverse n will give this h inverse z. That you can find out easily, because for what does it mean? This means that actually, you know, that if mod z is less than half, then actually this term becomes greater than 1. That is the problem. 1 by 1 minus x is 1 plus x square plus x cube plus dot dot dot. Now this 1 plus x square converges when x is less than 1. Otherwise 1 plus x square cannot be written as 1 by 1 minus x, right. So this term must be less than 1. That is the problem. So whatever summation you are doing, it should be such a summation that over which the 1 plus x square series is decreasing. So it will so happen that if you take n is equal to negative, then this series will converge to this value. you can just work it out. It's a matter of working out the series. Okay, but it turns out that this is clearly, first of all, unstable. Why it is unstable? Because n is negative, right? So it will kind of grow. Second thing is that it is non-causal because this is a negative index. So you see that it is not always possible unless you make that assumption. What I am trying to say is that unless you make that assumption, it is not always possible to get a unique Hn. So we will make that assumption very often because we are only interested in finding solutions which are causal and stable. We are not interested in finding other solutions. Okay. So now it says that a discrete time system is minimum phase if the system and its inverse are both causal and stable. That is a very nice result. It says that if you go from this way to that way, you have a causal operator, causal stable operator, you come back this way to that way, you have a causal operator. That is the kind of solution that we are looking for. They are useful to us, right? And so this is the definition of having a minimum phase. Many of you will come across this minimum phase, non-minimum phase business even in control. They are actually similar. And it turns out that if a system is minimum phase, if it's all its poles and zeros are inside the unit circle. And you can easily realize that if its poles and zeros are both inside the unit circle. So even if you invert it, if you from hz, if you go to 1 by hz, zeros will become poles and poles will become zeros. But if all are within the unit circle, then the inverse is also stable, right? So this is why we are interested in minimum phase solutions, okay, because we are always going to get stable causal things. This merely says that I will not do it. I will just say that, you know, there are some all pass filters. All pass filters, their magnitude response is 1 at all frequencies. Only their phase response changes, right? So for example, z minus a by z plus a, magnitude response is 1, but phase response will change with omega. Such filters are called all pass filters because they pass all frequencies with equal magnitude, right? Now it says that this result says that you take any hz, it can always be decomposed into two other hz's. One of them is going to be minimum phase, the other is going to be an all pass filter. Any hz, whether it is minimum phase or not, can always be broken up in this form. That is very simple to see because if you have any pole which is outside the unit circle, you have to just reflect it back inside the unit circle. This is so. Now why I am mentioning this result to you? Because this says now what is going to be the magnitude of hz? It is going to be the magnitude of this into the magnitude of this. This is a complex quantity, this is a complex quantity. So if C is equal to AB and ABC are complex, then mod C equal to mod A into mod B, right? So which means that corresponding to every hz, there is always a minimum phase system whose amplitude response is the same as hz, but whose phase response will be different, but magnitude response will match. So you can always find out a minimum phase system which will be, whose amplitude response will be equivalent to the amplitude response of hz. Why is that important? That is important because of the fact that, I'll skip this one now. That is important because of the fact that, remember that when we talked about, especially when we talk about random signals, which is of our primary interest, what do we want? What do we know? We know of power spectral densities. We don't know values. We cannot calculate just Fourier transforms. We can calculate power spectral densities, and power spectral densities are always related by hz inverse, or rather mod of hz whole square. If you remember that the power spectral density, if you feed a random signal input through a filter hz and get a power output, then the power spectral density of the output is related to the power spectral density of the input by this factor, magnitude of h e to the power j omega whole square. So the filter that you must use if you want to match power spectral densities, you only need to match its amplitude response. Phase response can be anything. If you want to match the power spectral densities, then you have to match the amplitude response. That is required. So you can choose phase response arbitrarily, which means that you can always choose a minimum phase response, because there is always a minimum phase transfer function which will match any amplitude response. So we will always choose, that is why we will always choose minimum phase transfer functions, because they are causal, stable and inverse stable. Okay. So you have to read these things. There is also a very interesting result called the spectral factorization theorem, which says that most power spectral densities can be factorized like this in terms of minimum phase systems. That is why most power spectral densities that you get in practice can be expressed like this, right? This can be done under some condition which is called the Paley-Wiener condition, mathematically speaking, but that is generally satisfied. It is not a hard to satisfy condition. So which means that most real power spectral densities, if you take a random variable and if you take its power spectral density, you can find out a spectral decomposition of that power spectral density. These things are important, because actually what we are going to do, we will get a random signal and we have to construct a model. How do we construct a model? Unless we can characterize its power spectral density in terms of a model, we cannot compute its model. So these results are going to be very useful in doing that. So we will stop here today. We will start with, we still have a little bit left, so we will start with the various kinds of models that we use and come to estimation very soon. Let us see, hopefully next class. I am promising, but I am not coming to the estimation problem. But the point is that the moment I come to the estimation problems, all these results are going to be used. So unless you at least know them, hear of them, we cannot. So that's all. Thank you very much.